Hello and welcome to our presentation on mineral waste, turning waste into value at Escondida mine. My name is James.
My name is Jude.
I'm Jonathan.
My name is Salman.
My name is Zakaa.
And we will be discussing our plan for extracting and processing minerals from discarded waste at Escondida mine, and how these methods can benefit both the mining industry and our planet. So, to start with our brief, we were tasked with evaluating the feasibility of remining and reprocessing the tailings, that is, the solid waste, from a mine of our selection within the Americas. Why is this necessary? Well, the first time that these rocks are mined, the mining company must decide which ores to extract metals from, and which ores are too low grade. This means that a significant amount of ores are discarded that still contain unextracted minerals. As well as this, a majority of mines specialize in extracting only one type of material, neglecting a whole host of metals and low-grade ores that nowadays can be extracted. In addition to the amount of value contained within these tailings, mining waste is one of the largest contributors of solid waste in the world. In the USA, 50% of all solid waste each year comes from mineral mine tailings. These must be stored in tailings dams, which can pollute the local environment as chemicals seep into the nearby ground. On top of this, tailings dams can devastate local human and wildlife populations if they fail, and this is occurring increasingly often. Reducing the necessity for tailings dams is not only profitable, as we will explain, it is also an environmental and humanitarian imperative. With all this in mind, our first task is to select a mine. Salman will explain our process for this.
Located in the Atacama Desert, Chile, Escondida is the largest producer of copper in the world. Over the course of 36 years, Escondida has now amassed a total tailings volume nearing 800 million cubic meters, shared between two dams. Copper mining and exports account for close to 50% of Chile's global trade market and is their primary GDP contributor. Ensuring the longevity and sustainability of this pillar industry could be augmented through tailings recovery practices within the region. The active and active dam are ranked 15th and 34th by volume globally out of 1,800 dams, with 50% of the world's total tailing volume being attributed to just 57 tailing dams from this range. Escondida presents itself as a prime example for tailings waste. Additionally, the data accessibility regarding the tailings mineralogy greatly improves the ceiling of technical analysis possible, making mines like Escondida the most effective way to investigate and tackle the crux of the issue of tailings waste. Majority owned by the BHP mining company, the current ore extraction process generates a 9,000 meters cubed an hour volumetric flow rate of tailings flow, which is directed into the active dam. The detailed tailings mineralogy shows that over 40 mineral varieties are present within the tailings slurry. The geographical location of the mine is in an arid desert region, and this presents a series of unique climate challenges which directly conflict with resource procurement and infrastructure. The Atacama Desert being the most arid region in the world means that water scarcity, sourcing and water distribution priorities are constant debating points within the Chilean political and social landscape. As the success of Chile's economy is predicated on the success of its mining industry, the allocation of resources raises challenging questions about the future of mining in Chile that need to be addressed. To better appreciate the scale of these large structures, the figure shows the span of the Laguna Seca Dam at its widest reach from the center of the university campus, and this spans a radius of 3.84 miles.
After conducting a thorough review of available extraction techniques in literature and in industry, having a goal of emptying the inactive dam, a compromise between high processing rate and reduced environmental impact was reached by combining a process possible at steady state with a high throughput and a batch process which can maximize the percentage of value extracted. These techniques are 1. Froth flotation and 2. Bioleaching, followed by solvent extraction and electrowinning, which are applied in tandem with a storage step in between. These maximize the process flexibility and value extracted from every kilogram of tailings. I'll pass on to Zakaa to give a more detailed process overview.
On the screen is a simplified flowchart of a proposed extraction process. As explained earlier, there are two existing dams at the Escondida mining site, the inactive and the active. Whilst the inactive dam is completely full of tailings in a slurry form, the active dam is continually filled at an inflow rate of 9,000 meters cubed per hour. A fixed continuous flow of tailings will be relocated from the inactive dam into a central mixing tank. At the same time, the tailings inflow headed for the active dam will be redirected into a second mixing tank. Both these mixing tanks will simultaneously output a constant flow rate of tailings into the froth flotation extraction process. This can be split up into 4 stages, which have different conditions and reagents. These stages are labelled FFA to FFD, and allow extraction of the 4 minerals displayed on the screen. After this has been done, the residual tailings are then pumped to the active dam, which is used as a temporary storage unit. From here, large batches of the residual tailings are pumped to the secondary bioleaching extraction process. Like froth flotation, different conditions, reagents, and microorganisms determine which element is extracted. These are shown on the screen. At this point, majority of the value would have been extracted. The remaining tailings will then undergo waste commercialization and be sold as aggregate to the cement industry. The tailings from the inactive dam will be relocated using a process called hydro remining. Essentially, this involves using remote-controlled high-pressure water cannons to dislodge the tailings, causing them to flow to the bottom of the dam. The inactive holding tank at the bottom of the dam will collect the water and tailings. The tank has two outflow pipes. The first pipe recycles water back up to the top of the dam, where it is distributed to the water cannons from a holding tank. The inlet of this pipe is fitted with a filter, which stops tailings flowing into it. A negative feedback control system will ensure that an external water source will top up and maintain the water level in the holding tank. The second pipe is responsible for pumping the tailings to the froth flotation process. This is a continuous process, and the inactive dam is expected to be completely emptied in 6.25 years. Salman will cover the second slide in the process, which is froth flotation.
Froth flotation is an extraction process for selectively separating hydrophobic contents from hydrophilic. For tailings recovery, the slurry is directed into a flotation cell where specific chemicals are introduced to function as surfactants, which enable the collection of a desired mineral. This is done by applying the desired mineral with a hydrophobic property. Then through air and density induced circulation instigated by an agitator, the hydrophobic minerals bind to the forming bubbles and rise to the surface of the flotation cell to be collected. This is done in a froth flotation arrangement in sequential steps of extraction and refinement, as indicated by the figure. The minerals being extracted are quartz, calcite, feldspar K, and wollastonite. These were chosen as the most effective minerals for targeting a reduction in the tailings volume while being balanced against mineral value.
After the desired minerals are extracted from the tailings, they are stored in the active dam. A select volume of tailings are dewatered and taken to the bioleaching process. Bioleaching has been utilized as a batch process in which bacteria/fungi are incubated and adapted to the tailings, then mixed with a select volume of tailings to extract the desired metal. This is done via the production of organic acids produced as the bacteria or fungi grow, which allow the metal to be isolated through ion displacement or formation of soluble metal complexes and chelates. After conducting the economic analysis of the most valuable elements available, and combining this with what was available in literature in terms of bacterial fungal suites and processing conditions for specific elements, the elements and compounds in order were chosen for extraction: copper, iron, zinc, tungsten, aluminium, magnesium, and silicon dioxide. The final product of this process is pregnant leach solution, in which the bacteria/fungi are full of metallic ions. This solution is then pumped to the solvent extraction and electrowinning process, which will be explained in more detail by John.
Solvent extraction is used to separate the leach solution into an organic layer of bacteria or fungi and a metallic layer. Each metal requires a specific solvent to cause the separation. Varying densities clearly separate the different layers so that the metallic layer can be siphoned off to the electrowinning cells. Electrowinning is an electrolytic reaction with the metallic solution acting as the electrolyte. By passing an electric current through the solution, the positively charged metal ions will be deposited on the negatively charged cathode to be collected. We propose using EMU cells, which are bespoke electrolytic cells that use a unique design where the electrolyte can be circulated rapidly around the anode and cathode, as you can see in the figure on the right. This increases the mass transfer, making the process more efficient, more tolerant of contaminants, and has a high production rate. After the process is complete, it has been proposed to commercialise the product by selling the residual tailings as aggregate in the construction industry. This gives additional income to the project, as well as encouraging environmental sustainability. This is because using tailings as an aggregate replacement in cement has been shown to reduce the carbon emissions of the cement manufacturing process. This has been demonstrated in a study which showed that a 30% aggregate replacement percentage results in a 22% reduction in CO2 emissions. Structural safety is of paramount importance, especially as tailings dams have been notoriously prone to failure in recent years. A recent study of serious tailings dam failures of the last 70 years showed that almost half occurred in the last 20 years. Key failures to be considered at the Escondida mine have been identified to be weak foundations, overtopping, seepage, and environmental causes such as earthquakes. A design failure modes and effects analysis, or DFMEA, was conducted to analyse the failures and recommend actions to mitigate against them. Historically, when dams have failed, primary criticisms have been poor maintenance procedures and management. Therefore, key recommendations were the implementation of a new monitoring and alert system designed specifically for tailings dams, and the application of a robust quality management system to ensure the quality of the dam and its foundations are maintained whilst the new process is implemented. Control systems have also been employed throughout the process to increase the level of safety. For example, there is a safety measure where vessels throughout the process are connected to the wastewater system, providing relief in the event of pressure build-up.
A life cycle assessment, LCA, has been conducted on the process to quantify its environmental impact. This began with scoping the LCA, followed by an inventory analysis where inputs and outputs of the process were identified. Because we aim to empty the inactive dam in 6.25 years, after which the throughput of the process and therefore the proportional environmental impact would change, the LCA method used was cradle to gate, with the gate chosen being operation and maintenance. Both reference databases for specific products and scale studies for process subsections have been used to evaluate the environmental impact potentials of the process. The largest potentials identified were the human toxicity and ecotoxicity ones. Using the CML database, these potentials were compared with values for different countries, and this further highlighted the need to prioritize a reduction in these, which will be expanded upon by Zakaa.
Air quality is an important metric that is used to measure the environmental health. The PM10 value quantifies the number of particles with a diameter of less than 10 microns. These particles can enter the lungs and can cause severe respiratory conditions. As shown in the table, the actual PM10 measurement is more than 6 times greater than the World Health Organization guideline. Due to this, it was a key priority that the extraction process has little to no direct air pollution. With majority of the process being done in closed environments, the only stage where particulates can be released is during hydro remining. However, this will be minimal as the water sprayed will trap most particulates. Another important issue that our process avoids is the seepage of toxic elements into groundwater. Once again, the closed nature of the process and the use of Escondida's existing wastewater system make sure that there will be no groundwater contamination. James will now cover the social sustainability aspect.
This project has the potential to benefit the local community in several ways. Firstly, the land currently occupied by the tailings dams would be made available for restoration. As well as this, BHP has a good reputation for enriching local areas through investing in education and community upkeep and providing employment opportunities. This project offers both the funds and the job opportunities to allow BHP to continue these promising community programs. Finally, the extra operations will result in increased tax contributions to the local government, allowing for Chile to further invest in these areas themselves. Furthermore, the process will have several effects on the mining industry, demonstrating the viability of extracting value from what has been considered a waste product for centuries could shift the perspective held by many mining companies, introducing an effort to empty other tailings dams and benefit both the mining companies and the environment. Furthermore, the extra materials made available through these processes would allow for more opportunity to keep pace with ever-rising global demands. Eventually, processes such as those discussed may erase the need for tailings dams, allowing for mineral mining to someday become a far more low-waste endeavour.
During process design, after sizing was completed, and due to the equipment used and the location of the project in the Americas, the Ulrich method was used to find the capital cost of the project, which came to $498 million. This is to be invested over 2 years. After calculating yearly income and operating costs, the project was found to yield a gross income of $3.74 billion, with a break-even time of just over 3 years. A very attractive discounted cash flow rate of return interest rate of 54% was obtained. This is mainly due to the very high throughput of the process, which maximizes revenue despite the high initial capital costs and operating costs. I'll pass on to John to talk about the next steps of the design.
Due to the vast financial and environmental benefits of this project, the team would strongly recommend pursuing this process design in the future. Going forward, there are several steps that could continue to progress the project. Larger testing samples in pilot studies for reprocessing tailings can verify the project's feasibility. This should also give a more accurate estimate of the recovery efficiency that should be expected from the process. This can be further informed through an on-site analysis where the terrain and profile of the land can be examined so that the layout of the necessary equipment can be outlined in detail. An investigation into the likelihood of process stoppages and how often mining processes have had to be halted in the past at Escondida would be required. This can lead to more accurate estimates for the project timeline and subsequent financial analysis. The team incorporated a variety of project management tools and techniques to aid in the successful execution of the project. A detailed Gantt chart was created to distribute work and manage the project schedule. The Gantt chart was reviewed regularly to ensure the project was progressing to meet the necessary deadlines. Due to the vast nature of the project, it was imperative to store all files and important resources in a central file directory. This was done using Microsoft Teams, a tool that everyone in the team could use to edit documents collaboratively. The team employed agile working techniques with regular stand-up meetings to maintain high levels of communication throughout the project. This allowed for frequent and reliable feedback to guarantee the project was completed to a high standard.
We would like to take the time to thank our project supervisors who have been instrumental in the development of this process, Please feel free to ask any questions to the project team for more detail.